Hey, welcome to the greenhouse. I'm Alex. Let's talk about light and the different wavelengths that it propagates at and how it interacts with different things in the environment. Come on in.
Different forms of light, or radiant energy, are characterized by their wavelength. To use a familiar example, think about the colors of the rainbow. When visible light is broken into the color components that make up the rainbow, each color represents a different wavelength, between 400 nanometers for blue and 700 nanometers for red. You may have noticed that when you see a rainbow, blue and purple are always on the bottom or the inside of the rainbow, and red is always on the top. This is because the different wavelengths of visible light behave differently when they interact with different materials. Blue has a shorter wavelength than red, and it's bent more when it's refracted by the raindrops that create the rainbow. We see the same thing when sunlight is reflected by a glass prism.
There are lots of other wavelengths of light that our eyes can't see. For instance, really short wavelength ultraviolet, and then much longer wavelength infrared. Infrared is really important because of the way that it interacts with gases in the Earth's atmosphere. Visible light and infrared light behave differently when they encounter different materials in the environment. So we're going to use our phone-mounted infrared camera to explore some of this behavior. Now, I've got a picture frame here, and it's got a piece of glass in it. We're going to take a look at how the visible and the infrared light behaves when it encounters this piece of glass. I've also got some other materials. Here's another picture frame, and across that we've stretched a piece of plastic food wrap. And then on the third frame, this is just a piece of black plastic trash bag stretched across there. So we're going to take a look and see what we can see.
Okay, let's start with the clear plastic wrap. I'm going to stand it up and put a clip here, and then when I put my hand behind it, I can see my hand behind the frame. If I switch the camera to infrared, I can still see my hand. The infrared energy that my hand emits is passing through the plastic wrap to the camera, so the plastic wrap is transparent to both visible and infrared wavelengths. All right, let's switch to the glass. Again, glass is transparent to visible light, and I can see my hand behind the pane. But now when we switch it to infrared, whoa, my hand disappears. Unlike the plastic wrap, the glass is absorbing the infrared that my hand emits, and we can't see it anymore. All right, finally, let's look at the black plastic. And let's think about this first. What do you think we'll see in both visible and infrared light? Make a hypothesis. If your hypothesis was that the black plastic absorbs the visible light that's reflected off my hand, yes, you're correct. It does. We can't see my hand. All right, how about in infrared? Hey, look at that. Just like the clear plastic, the black plastic is transparent to infrared. That's kind of cool. So we've got clear plastic that's transparent to visible and infrared light. We've got black plastic that absorbs visible but is transparent to infrared.
And glass, which is transparent to visible light but absorbs infrared. Interestingly, it's this property of glass that gives us the term greenhouse effect when we talk about Earth's climate. The glass in a greenhouse, like this one, is transparent to incoming visible light, but it absorbs the outgoing infrared energy emitted by everything in the greenhouse. This is one reason why the greenhouse is warm, and this same process happens in Earth's atmosphere, where most gases are transparent to visible light, but some gases, like carbon dioxide or methane, absorb the outgoing infrared radiation that the Earth emits back to space. So understanding how different kinds of energy at different wavelengths interact with different things in the environment is really important to understanding Earth's climate. How cool is that?